The fabric of space-time as we understand it is a delicate structure. It bends and stretches, but there's a limit to how much it can endure. If that limit is reached too quickly, everything could unravel. Now, in the grand scheme of the universe, this could have devastating consequences that could change the very face of our night sky. Our skies, which have remained a reliable source of navigation and wonder, are rapidly transforming, and in a matter of a few years, or possibly sooner, our skies could become utterly unrecognizable. Cosmologists across the globe are sounding the alarm. Renowned specialists, including Neil deGrasse Tyson, have recently confirmed something rather unsettling: the inevitable explosion of Polaris, our beloved North Star. Polaris has long been a constant in the heavens, a guiding light for sailors, astronomers, and stargazers alike. It's been a cornerstone for celestial navigation, an unwavering fixture in the northern sky. But this stability, this familiar presence, may soon be disrupted, reshaping our night sky and possibly altering our understanding of galactic measurements. It's time to delve deeper into this looming threat and explore the potential consequences of Polaris's eventual demise. For centuries, Polaris has been the navigational beacon for seafarers and explorers, its fixed position offering a sense of direction in the vast expanse of the night. But now, this seemingly unshakable presence is facing an uncertain future. In September 2023, the Royal Astronomical Society released a research paper suggesting that Polaris is on the brink of something catastrophic. It might soon explode, vanishing from the night sky forever. Before we jump into the potential aftermath of this revelation, let's take a closer look at Polaris itself. Polaris, or the North Star, holds a unique place in the sky, primarily due to its close proximity to the celestial North Pole. Positioned directly above Earth's northern axis, it appears almost stationary in the sky, making it an indispensable tool for navigation. Located in the constellation Ursa Minor, or the Little Dipper, Polaris is a yellow-white supergiant, much larger and brighter than our own Sunday. However, Polaris is not a single star. It belongs to a complex triple star system. The two primary stars, Polaris A and Polaris B, form a double pair, with Polaris B orbiting around them. The interactions between these stars create intricate gravitational forces that govern their orbits, influencing the behavior of each component. Any disruption in these interactions can lead to irregularities in the star's brightness or changes in its pulse patterns. Despite our understanding of these gravitational forces, the exact mechanisms driving them remain somewhat elusive. Polaris is situated approximately 323 light-years from Earth, which means the light we see from it today has traveled for more than 3 centuries. If Polaris were to explode now, we wouldn't even notice it until over 300 years later, giving us plenty of time to speculate. In fact, it's possible that Polaris has already exploded, and we simply haven't seen the light from that event yet. Throughout history, Polaris has held immense symbolic, navigational, and cultural significance. Its consistent, unchanging position made it a prized guide for ancient sailors, helping them navigate across vast oceans and unexplored lands. Symbolically, Polaris represented stability and direction, a steadfast presence amidst the chaos of the universe. For astronomers, it has served as a crucial reference point, aiding in the study of celestial movements and variable stars. As a Cepheid variable star, Polaris exhibits regular fluctuations in brightness, which has provided astronomers with valuable insights into the properties of stars and the nature of stellar evolution. These pulsations have also played a vital role in determining astronomical distances and calibrating various instruments. Its predictable behavior made it a fundamental constant in the astronomical community, allowing us to measure and chart the cosmos with remarkable accuracy. However, recent observations suggest that Polaris is no longer behaving as it once did. Instead of following its regular, expected pulse pattern, Polaris has started to display erratic dimming, raising concerns among researchers that it may be nearing the end of its life. This anomaly in its pulse cycle aligns with the behaviors often observed in stars on the brink of their demise. The gradual stretching of Polaris's pulse period, which used to remain steady, is indicative of internal changes. In fact, there has been a measurable increase in the pulse span by 4.5 seconds annually. While this may seem minor, it carries significant implications. Some astronomers suggest that these variations could be due to gravitational interactions between the stars in the Polaris system, which may be altering the star's atmospheric conditions and directly influencing its pulse patterns. Others are more alarmed, believing that Polaris is nearing the brink of a catastrophic event. The similarities between Polaris's current behavior and that of Betelgeuse, a famous star in the Orion constellation, are striking. Both stars have exhibited unusual fluctuations in their luminosity, sparking fears that they may be on the verge of exploding. As stars in their twilight stages often show similar irregularities before they reach the end of their life cycles, it's no surprise that NASA has expressed heightened concern over Betelgeuse. However, Polaris has largely flown under the radar of formal attention, despite showing signs that it may be heading down a similar path. Like Betelgeuse, Polaris is a massive star nearing the end of its life. When stars of this size reach the end of their main sequence, they go through various stages, including the red giant phase, before ultimately culminating in a supernova explosion. Polaris's irregular pulsations are suggestive of a star in the advanced stages of helium depletion, a process typical of giant stars approaching the end of their life cycle. While these abnormalities fit the profile of a Cepheid variable star nearing its final days, definitive evidence that Polaris is on the verge of a supernova remains elusive. Nonetheless, astronomers are closely monitoring these peculiarities, hoping to better understand Polaris's fate. If Polaris were to go supernova, the event would be an extraordinary spectacle, potentially outshining the moon and becoming one of the brightest objects visible in our sky for days, weeks, or even months. Such an explosion would dramatically alter the appearance of familiar star formations, such as the Big Dipper and Ursa Minor, to which Polaris belongs. However, despite the spectacle it might create, Earth would be safe from any immediate dangers due to its vast distance from the star. While a supernova in Polaris may not be as visually dramatic as the anticipated explosion of Betelgeuse, it could still be visible to the naked eye for an extended period, outshining nearby stars and capturing the attention of astronomers and stargazers alike. Although the event would have little effect on Earth's climate or environment, its significance in the astronomical community would be immense. As Polaris approaches its final stages, rather than a dramatic supernova explosion, it's expected to meet a quieter fate, transforming into a small, incredibly dense remnant known as a white dwarf. This is the final form for stars of low to medium mass that have exhausted their nuclear fuel. Despite its significant mass, a white dwarf is about the size of Earth, making it incredibly dense. The mass might resemble that of our Sun, yet it's packed into a space no larger than our planet, which is an astounding density. Over time, such remnants become invisible to us here on Earth, just as we currently perceive Polaris. In essence, its once brilliant light would fade, leaving behind a dim, imperceptible celestial body. To fully grasp the magnitude of such a transition, we can contrast it with the aftermath of past supernova events. By comparing the expected behavior of Polaris with historical supernova events, such as SN 1987A, SN 2011 Fe, or SN 2014J, we gain valuable insights into stellar evolution. These events, like SN 1987A observed in the Large Magellanic Cloud, have already provided profound understanding of the life cycles of stars and the dramatic consequences of their deaths. These supernova remnants, like the Crab Nebula formed by SN 1354, are rich fields for study, expanding and emitting radiation across various frequencies, offering a clear picture of the violent aftermath that stars like Polaris might one day undergo. Through these supernova explosions, we learn how stars eject vast amounts of material into space, creating nebulae and enriching surrounding interstellar gas with heavy elements. This process contributes to the ongoing cycle of star birth and death in the universe. The energy released, in the form of powerful shock waves and beams of radiation, also plays a crucial role in shaping cosmic radiation conditions. This has broad implications for the evolution of matter and energy in our galaxy. The study of light curves, spectra, and remnants from events like SN 1987A allows astronomers to predict similar characteristics for Polaris, offering clues about its eventual fate. When examining such events, we focus on key factors such as the mass of the star, the velocity of the material ejected, and the nature of the explosion. These factors give us a clearer picture of the potential impacts of Polaris's eventual transition. The study of these stellar remains allows us to make predictions about whether Polaris's explosion will lead to the creation of nebulae, the distribution of heavy elements, or any other unique outcomes. The data gathered from previous supernovae provides crucial insights into what we can expect from Polaris when it eventually exhausts its nuclear fuel. Another important area of research is the pulsational variability of stars nearing the end of their lives, such as Polaris. These pulsations could indicate internal instabilities or the onset of a catastrophic event. Studying the pulsations of stars like Polaris in comparison to supernova precursors is key to understanding the complex processes leading up to these explosive deaths. The observed irregularities in Polaris's pulsations suggest that it might behave differently than expected, presenting an interesting challenge to astronomers and requiring them to reassess current models of stellar evolution. These unique behaviors may reveal unexpected mechanisms behind the explosive events that stars like Polaris will ultimately face. Despite the extensive research and careful observation, astronomers continue to encounter anomalies when studying Polaris. These irregularities suggest that its behavior is unlike other stars of similar size and age. By delving into the underlying mechanisms of these pulsations, astronomers hope to gain a better understanding of the forces at play within these late-stage stars. This pursuit of knowledge not only furthers our understanding of stellar evolution but also opens the door to new theoretical models that could reshape our conception of the universe's life cycle. It's these breakthroughs that could pave the way for future discoveries, helping us to understand more about the life, death, and rebirth of stars in our galaxy and beyond.